Welcome back to the HVAC Engineering Techie channel. This is a channel where we talk all things HVAC. We talk engineering design, construction, equipment systems, test and balance extensively, controls, efficiency, and performance. These videos are intended to be educational in nature to help you in your career and on the job. Today we're talking about TAB again, test and balance of pumps and balance valves. Exactly how do you balance a pump correctly? And how do you balance a valve? Now that sounds strange, but balance valves are a little bit different creature. We're going to talk about them today. So before we start, if you're new to the channel and you like this training and you really want this training, do me a favor if you would and become a subscribing member by pushing the black button down below. It's absolutely free. It's no cost. It's painless to you, but it's really beneficial to me because Google uses that to evaluate the channel, and I would really appreciate it. So thank you for that. So let's get started. And by the way, if you have other friends and technicians who could use this training, give them a hint. Send them a link to this or a copy to it so they'll know that you're enjoying it and maybe they would too. Thank you. Let's get started. So first we're going to talk about pumps and exactly how you balance those and what steps you have to take to do that. All right, this is a typical pump. This happens to be an end suction pump. They do make base-mounted pumps and inline pumps and many pumps that look different, but they're mainly all centrifugal pumps that we deal with. So this is got a suction pipe that comes down, and this particular one has a suction strainer. Your job may not have a suction strainer here. It may have a regular Y strainer up here that has a Y down this way, and it may have an elbow here. If it does have an elbow, it really should have the if it needs a transition because it's different size, it must be flat on the top and slanted on the bottom. And the reason for that, if you put a bell mouth on there, it could entrain air bubbles and cause a cavitation of the pump. So best practice is it's flat on the top. Okay, so then this goes up, the discharge goes up to we have some isolation absorbers on here to prevent the pump vibration from going to the pipe. We have a normal check valve, and we have two shut-off valves. And I forgot to turn them on. There's the shut-off valves. There's the check valve. And these are the pressure reading ports. So this is a header. This is how we really like them to see them. A designer may not do that. A designer may put a gauge here and a gauge here. And if that happens, then you'll need to revise that. When you go to balance a pump, we need a reading on the discharge of the pump here, and we need a reading of the discharge of the pump here, or a suction of the pump here. So we can't have them out here. Now, you see here, we have one here, but this is designed to close this valve and open this valve and take a reading before the strainer and take a reading here of the pump. And then you can get the differential pressure across the strainer to tell if it's dirty. Need to know if you need to clean it. So if they have two gauges, what we normally do is take one gauge off if you're using gauges and use it both places. Then that way we take away any discrepancy in calibration between the gauges. But more than likely, you will hook up your electronic gauge to this, and so you can just hook up your gauge to this port and then use these headers as required, and you'll only have one gauge that way. Now, I'll talk about my pet peeve right away so we don't have to get into it later, is you never, ever need a balance valve on a pump. It's ridiculous. It's ridiculous to think you need a balance valve on a pump. Remember, a pump is basically a metering device, but we also have balance valves downstream. So if you have a balance valve on a pump, you actually have two balance valves in series. Makes absolutely no sense. And the other reason not to put a balance valve there is because someone will use it. And what I'm saying by that is, all it does is induce a system pressure, which costs you horsepower, which costs you energy forever. Best practice is never, ever to have a balance valve on a pump. I guess unless there was only one thing a pump was feeding and you didn't want to put anything downstream but whatever the load was, you could put it here. But it's nonsense. It really needs not be there. And the reason I bring that up is because the pump manufacturers, in their instant wisdom trying to sell stuff, created triple duty valves. And the triple duty valve takes the place of a shutoff valve and the check valve and a balance valve all in one valve. And they sell them to contractors saying this will save you money because you only have one set of flanges to do. You don't have 3 sets to do, only one. It'll save you a bunch of money. But the truth is, we don't need them. We don't need them. We don't want them. And here's the second reason not to ever specify or try to put in a triple duty valve. There are different kinds of triple duty valves. There are a certain group of them that have shafts, stainless steel shafts, and comes out in they rotating device, and you screw them in or screw them out to adjust that valve flow meter inside the valve. There are other ones that just have a hand wheel and has a gear rotation in there. Those are fine. They don't screw up. But I tell you, the ones that have the stainless steel shaft you screw in and out, in a couple of years you can't move it. I tell you that somehow the rust fines gets inside that packing, and they become impossible to open and close. So they're not very well made. They're not manufactured correctly for the service, and I would never ever use one. And I know this by experience because I have spent hours with a big wrench and a big pipe on a cheater bar and taken hours to open a valve or close a valve. So basically, don't ever use them for a close-off valve. If you got to use them for anything, I guess a check valve, you get, well, why would you? They cost 3 or 4 times more than a check valve. So, okay, I get off my soapbox. Don't use triple duty valves. Okay, so first thing you do when you're going to balance one of these, you start the pump and take the inlet and discharge pressure readings to establish a pump flow. So you're going to take a pressure reading at the discharge and a pressure reading at the suction. And remember, they have to be exactly in the suction. A lot of times when you get to a job, you'll realize the contractor actually put this connection up here, and he put this connection over here because it was easier to get to. Can't use it because it has these components within the measurement stream, and then you can't use those readings to look at a pump curve because you've got extra pressure in there. You can't calculate it away. You can't do anything. You're just stuck. You basically cannot use a pump for flow. I mean, to read flow for a pump, you can't use a pressure differential. So those have to be installed correctly. And if they are installed correctly, you need to make a big fuss and make sure the contractor changes those because they're not only no good for you, they're no good for the owner later on. So they need to be changed. And by the way, we see them wrong all the time. So total pressure equals the discharge head minus the suction head. Now that may not seem too intuitive to you, but it's that way just in case, you happen to have suction pressure below 0. And if you do, then it becomes a plus and it adds it to it. But otherwise, if you have 10 psi coming in here and you have 50 psi going out, the differential is 40 psi. So the equation is really simple. So balance, once you get that all set up and it's got the flow you want, then you balance the valves to adjust the flow. So you go out and adjust whatever your loads are, you adjust the flow for that. Now this may be flowing more water than you want, but you go balance the load. Now it's our intention always when you balance the load to use the lowest practical pressure, which means one valve will always be 100% open. That way you know you got the lowest practical pressure. And you balance it so you got it. Now if everything's a little high, then you come back and change the pump. Now how do you do that? Well, if you're going to balance it and you have no way to do it and you're 3 or 4% over, don't worry about it. Just leave it there. You can run high. High is not a sin, right? Real high is because it's using horsepower, but if you're 10% high, 12% high, it really, that's not a problem. If you're 40% high, okay, now you got to make a change. And what you really need to do is trim the impeller. Well, to trim the impeller, you have to know what impeller size does it need. That's the key. So how do you do that? If you look on your pump, the impeller size should be labeled on there, but you need to check it. So here's how you check it. You close off the discharge valve, leave the suction open, close off the discharge valve, and take a suction pressure reading discharge and suction reading to determine the head. So basically, you should have no flow, 0 flow, because you got the valve closed, 100% closed. And the way you can do that, you can start the pump with the valve closed, or you can have it open and then slowly close the valve. You just don't want to, close it really fast because you might shock the system. But you close it, and the pump can run that way for a few seconds or a few minutes, not a very long time, because now you have this pump deadheaded. So all that horsepower in that pump is going into the water. What I'm trying to tell you, turn it to steam very quickly. So you can't run it with the head closed for any extended period of time. Just a few minutes, enough time for you to take these pressures, the suction pressure and the discharge pressure, then open the pump back up. Now, you take that data And once you've got that on the curve, and we'll look at this in a second, you can actually determine what size impeller it has, and then you'll calculate what size it needs. And then what they do is they have to remove it from the pump and trim it on a lathe, and then send it back and install it. Now your pump will have the right characteristics to match the load. And the reason we do that is because if you just take this valve and you close this valve off halfway to induce enough head to make this flow correctly, that's costing horsepower, and it'll cost more energy forever. And so that's not the right way to do that. Okay, if the pump is a constant volume, determine if the impeller needs to be trimmed. If the loads are balanced to the lowest practical pressure with one valve 100% open, and all valves are over 10% flow, then impeller needs to be trimmed. If variable flow, just simply adjust the speed, right? If variable flow is no problem. All right, so here's our pump curve. So remember that here is the head, and this is the flow, and you've made a pressure reading. So you've got a differential pressure. This is the pressure, total pressure of the system. It's in feet, it's in head. So if you had about 63 foot of head, then you would have an 8-inch impeller, because your flow is 0. So here's the 0, and you read your head, and that's where your impeller is. So that's where it needs to be. Now, why do you need to do that? Well, sometimes pump manufacturers aren't perfect, and what is on the label is not what's in the pump. Because these pumps all come, when they manufacture them, they're manufactured with the largest impeller that pump will handle. And so then to get ready to ship your pump, they have to trim the impeller. And so they do. So it's all kinds of different inches. Now, what you want to know is if you need 400 GPM at, say, right here, which would be if they've done it correctly, they should have provided you a 7.9-inch impeller, maybe, because right here's an 8-inch impeller curve. And so how you find that is you get your GPM, you get your head, and you go across the head until you hit that curve. If you got an 8-inch, then right here would be the flow that pump is capable of at that head. Now, many times the design may be here. Your design may be 300 GPM at 70 foot of head, and you don't actually have that. When you go out and measure it, you only got 60 foot of head, so it'll actually do more flow. It'll 450 or something like that, which means if your balance doesn't actually take some of that out, when you do the field balance, you actually cause back pressure in the system, and you will lower flow. And that's why I always say try to set the pump up a little higher so you got some room to back up that pressure up the curve so it'll work. So this is how we find out where we're at. Now, if you need to do different, then what you do is if you've got, right now your pump system is pulling 400 at the pressure you need, and you only need 300, then you just go over here and you notice that, okay, it was here at this 8-inch impeller. Now I need a 7.5-inch impeller, or it might work out to 7.6. Now, you say, well, I can't actually see that on this curve. So, how do I tell it to get it to a tenth of an inch? Well, you just use percentage. So if you need to change a percentage, if you between this and that, you got 10 points, you need a certain percentage, then just percentage the difference between the lines, the same percentage, and you'll come up to the tenth you need. It's not too hard to do, and cheat just a little, and I always add a tenth of an inch to it. So just in case there's anything leeway at all, I've still got enough water to do what I need to do. So that's how you balance a single pump. It's not hard. And so the hardest part is determining if you're going to trim an impeller. Now, I got to tell you, your contractors are not going to be happy for you to recommend you trim the impeller. Now, if they decide not to trim the impeller, there's nothing you can do about that. Someone may close the valve a little bit to bring the pressure down or not. Another reason not to put a balance valve on or to try to balance down at the pump is because sometimes you're right on the curve, and if you allow more flow, then you put the pump amps over its rated amps into the shoulder. And if you do that, you risk the chance of someone, if you've got that discharge valve balanced down, you risk of someone coming on and working the pump, and they open that valve full, or they close it down to work on the pump, and then they open it full because they don't know where it was. And then you could actually maybe go into overamp. So, I mean, it's a bad idea to use that valve as a balance valve. It's better to trim the impeller or to balance the load down in the field. I had a customer that insisted not to trim the head because they didn't want to spend any money, or the contractors not spend any money, and you've told that owner this is basically going to cost you money and energy forever, and they don't care. And the right way to do it is not mess with the pump. Go out to the field and lower the valves. So basically, you're going to induce more head than needed out at the valves because you can always balance the load. That's what I'm trying to say is why you don't need a balance valve at the pump. And then you'll be okay. You're not the lowest pressure, but they didn't want it lowest pressure. So that's their decision. They have to live with it. So now let's talk about balancing multiple parallel pumps. So normally if you have two pumps, normally you have one pump as lead and another lag. So that means that the lead pump runs and carries the whole load unless it fails, and then it switches over to the lag pump, giving you 100% redundancy on the project. But it is possible for an engineer to not design it that way. He can design it so that one pump carries 50, 60% of the load, and then when it gets over that, it turns on the second pump, and they're staged pumps. The only way to tell that, because the engineer doesn't tell you, is to add up all the coil loads in GPM and see how that matches one pump. If the GPM coil is less than or equal to one pump, then you have a standby pump. If the GPM is a lot more than one pump, then you have stage pumps. So if you have stage pumps, you have 1 and 2, and you know they don't run together, then you just balance one pump and then switch over and balance the other pump to make sure they're the same. Test one pump to test the other to make sure they're the same. That's all you do. However, if you've got stage pumps, then what you have to do, you have two pumps to run together, then start both pumps and take inlet and discharge pressure readings to establish pump flow. So when you get both these running, you take your suction readings, they'll be the same. You take your discharge readings, and they'll be the same. So now you know that you've got your pressure readings of both pumps. Now, why do we do that? Why don't we just balance one pump and then balance the other pump? Because if we're running 50% flow in the system, the pressures will be way, way down, and so it won't be the right good connection to the pump. If they're both supposed to run, then you have to put them together to take the readings. Now, what if you have three pumps? Well, that means that the third pump is standby to one of these others. So you know that you have 50%, roughly 50%, 50%, and then you have a standby 50%, so you're still good for standby. You assume that you're not going to lose two pumps together. Balance, always go out to balance the load, and then close the discharge valves on both pumps and take the suction pressure and discharge pressure. So these should have the same impeller, but you can do one at a time. You can do them together. It doesn't matter, but you just read the discharge head and the suction head and find out where you're at on the curve to figure out where the impeller's size are. Turn off the second pump and turn on the third pump to verify pump reading. So once you've got these two balanced, turn one off and make this the second pump and make sure you're still the same. That when these two running, you have the same pressures as when you have these two running. Find the shutoff head of the pump curve by dividing flow by 2 and read the average head. The pressures are fine. You don't need to do that. But here's the curve to say what I'm talking about. So when you have multiple pumps running together, parallel pumps running together, you need to request a multiple pump curve. So normally a pump curve is for one pump, and this one here would be one pump. So this would be the shutoff head right here, and this would be the total flow of the pump at no head. So you can see that's the one pump curve. Well, we have two pumps, so since they run together, we need the second curve, which is the second pump, which is the same head, right? And it goes out here. So where this no head flow from here to here, from A to B, is the same as from 0 to A. So these are equal here, but as this curve comes back up, and I didn't draw that very well, then these change position. What I'm trying to tell you here is that this GPM is less than this GPM. So the second pump doesn't add 50% of flow. And that's where people some engineers will mess this up and think that they have two pumps, you get twice the flow of each pump, and you do not. This is going to be about 10%, 10 to 15% less. You add a third pump, it'll be 20 to 25% less. You add a fourth pump, it'll be 40% less. So it gets less and less flow as you go. That's why we only see three pumps. more is getting foolish because you get less and less for your money in energy as you go out. So normally 2 pumps running together is okay. 3 pumps running together, maybe, but 4 is ridiculous. You never do that. I did have a project one time, which was a retrofit project for a big civic center, and it had 8 secondary pumps, which means that 8 pump, it was just spinning. It wasn't actually doing anything. They didn't do it on purpose. It had a whole bunch of remodels, and every time they remodeled, they'd add a space and add another secondary pump. It made sense to them, but really they were headers, so it was very bad. The right choice would have been put bigger pumps in and still have 3 pumps. Anyway, that's how you do parallel pumps. Now, where do you get this curve? It should be in the submittal. If you're running 2 parallel pumps, I got to warn you, it probably won't be because the pump supplier doesn't really know whether they're running parallel pumps or not either. So what happens is you request and the vendor can create that curve. It's on their computer. They just push a button and they can create a 2-pump curve. And that's what you need to really evaluate the system and to know really where it's running on full GPM. All right, what about series pumps? Now, series pumps are a little different and you may not see them very often. They are used mainly in industry and in maybe high-rise applications. And these basically have 2 systems in series. So the water flows into one and it raises its pressure, then that flows into the other and it raises its pressure, and this is the total pressure going out to the system. These may also be with series chillers. So there may be a single pass-through chiller here and a single pass-through chiller here. It's kind of a unique kind of system that have those. I have seen those before. So this is a series pumps one, and these are easy. These run together, right? They always run together. They don't run separately. So if 2 series pumps run together, start both pumps and take the inlet net discharge reading and establish the total flow head. So you turn both these pumps on, and you take your readings. So here's readings 1 and 2, and a second and third pump, and then you add those together. Basically, is how you get total of the pump. So total pressure equals the pump A discharge head minus the suction head, and pump B discharge minus suction head. Total flow, total pressure plotted on a factory 2-pump series curve. So this is the same. You have to get a 2-pump series curve to tell really where you're at. And then you go balance the load just like always. And and then you need to find the impellers, and you have to do each one of these separate to find the impeller. So you just close off this one and read the discharge and suction, and then close off this one and read the suction. You need to figure out where you're at, and then you do the impellers with the pumps. So this is a 2-pump series curve. So you see that this is 0 flow shutoff head for pump 1, and then you add shutoff head for pump 2 here. So this piece here and this head here are equal. So the 2 heads, in other words, at 0 flow, the second pump does add a second pump head. But the problem is we have this curve. And the curve is, this is a single pump flow at 0 head. Okay, but this second pump is the same. So this curve goes to here, and this curve goes to here. So it's the same as the other thing. It's just standing upright instead of laying down. Pump number 1 does this much head, and pump number 2 does this much head. And these 2 are not equal again. The second pump will have less flow than this graph may not look like it shows it, but that's because I've drawn it by hand. So this has the same problem, is the second pump doesn't double the head. It's less than double the head. So you have to do that. You have to use this curve to tell the total head at total GPM for the system, head. So that you got to do that. So request a curve. All right. So now we talk balance valves, which are much easier than pumps, especially if they're multiple pumps together. All right. Now in this time, I'm going to talk about specific manufacturers of balance valves because they're all slightly different. And we'll talk about them all, but I'll talk about the 3 or 4 big ones, and then we'll talk about the generic. So the first one is called a Bell & Gossett Circuit Setter. They were the first ones to produce this valve that I'm aware of. And this is a typical valve. They make a whole bunch of different kinds and all different sizes. And they have a little gauge out here that tells you what the setting is of the valve, and it's lockable. So you can turn this thing and then lock that screw, and it locks it in place. So someone can't inadvertently try to use it as a shut-off valve. Now, they can take a screwdriver and turn it, but hopefully your balance report will show you where you put this, because it should show this symbol here where you did that. Now this one's an easy one. It's A, B, C, D. Or this is numbers. And this one's actually numbers percent opening. Okay. So here's a circuit center sizing chart. This is a particular one, how many GPM it handles, and what the size of valves are, and what its CV value is. Now, you don't really need to know the CV value, and we're going to talk about how you do that. Now, Bell & Gossett made this, we call it a circuit center, and it's a slide rule, round, of course, but it's a slide rule to help you set up these valves. And side one is side for presetting only. They got looped around the axle on this and said, yeah, we're going to use this so you can go in and you can preset all the valves and then go install them in the field, and they'll be already field balanced. Well, yeah, it's true. If you go read the instructions on doing that, you're going to say, no, I'm not doing that. Because you actually have to calculate the entire pressure of the system at every single valve. And, the inlet pressure is different based upon the pipe characteristics. You have to actually go through an engineering exercise to do this. You might even have to do a Hardy loop calculation if you have any loops. I mean, it's a tremendous amount of work that you and I are not going to do, I guarantee it. Now, if you have one valve, sure, no problem, because you can tell what the inlet pressure is going to be, but if you cannot, it's hard. Now, side two, so first thing you do here is you set the flow and head. And so it has up here the flow and the head, and this is the total pressure. And so if you know that, if you know what your pressure is on the system, then you can do it. And here's the problem. For using this as a preset, you can't tell it. And then the second reading, of course, is read the valve setting for size of valve. So if you have a 2-inch here, I think it's 1.5 inches. I can't see that very well from here, 1.5 inch valve. And where that line is where it should be adjusted to. To get this flow at this head, you need to adjust the valve to there, which is fine. But normally we don't know that, right? So we need to use side two. I think it was Armstrong was Bell & Gossett Canada or something. I don't remember the details, but it was. Now this is their balance valve. They make all kind of the big flange valves look slightly different, but this has a wheel that it's got markings on the wheel, and you turn it. And this is your orifice down here where you're measuring flow across an orifice. And this is real simple. You've got these graphs, and you can see that this is your flow, and this is your pressure, and this is your hand wheel position. These reach for a size of valve. Like this is for 1/2 inch, this is for 3/4 inch valve. So if you're going to set it at 0.5 and you read a pressure here, then you go over 0.5 and down to your flow. So you don't need a calculator for that. You can just look at a curve. That's all you need to do. Here's another one for a range of different kinds. So this is a bigger valve. And they make this balance chart for each size of valve. So you just, in the submittal, it should have been in the submittal for you. And you can balance this valve and read this valve directly from there. Taco makes one. So this is, you're reading pressure across the orifice, and you're adjusting here, and you can lock this one down. And again, it's just like the other one. It has the valve sizes, and it has, this is the valve sizes, and here's your pressure reading down to. So basically, when you go to the field, you hook it up to your instrument, read the flow, adjust the flow, and read it to where you get it, and then you're done. All right, now we're going to talk about automatic balance valves. So they have automatic balance valves that were built to self-balance the system. So you put these on downstream of a coil, and they're actually spring-actuated valves. So they have a little cup in there with a spring behind it, and as the flow pushes it in, it has slots that get bigger or smaller and let more or less flow in. So they do work. There's a couple of things you have to consider about automated valves. They do work fine. One is they do increase system pressure because you're always pushing against that spring, and that's some pressure. Might not be significant, but it is pressure. It does cost money to run forever. And secondly, the more important thing is, which most people don't realize, and I probably ought to look at, okay, it must be ordered for a specific GPM or GPM range. So you just can't take a valve, say I got a 3-inch pipe, we'll put a 3-inch one in there. It has to be selected for the pressure differential and the flow you want it to control. The second thing is limited pressure range. If most of these are selected from 2 to 32 psi, so it means if you have less than 2 psi across that valve, it's now a fixed orifice. It won't actually adjust the flow because you're out of the spring range. You haven't even started to push the spring yet. It's all the way over. 32 psi is a maximum. If you get over 32 psi, it's pushed the spring all the way back, and now it's fixed orifice. This is where, as a balance contractor, you need to actually look at these. And most people say, oh, I've got automatic valves. You don't need to balance it at all. That's not true. You need to balance the pump, and you need to verify the pressures in the field are not exceeded these valves. If they're exceeded these valves, you have to have a valve in front of them to balance them down, so that maximum pressure, the valve won't see the maximum pressure. Or else you can just let it be an orifice, either way. So they do come in different ranges. Some are 1 to 14. They have different ones. There's I think it's 5 to 50 psi. There's different psi ranges, but I don't think most contractors know that. They just install them because it's automatic. I don't need to buy balance. They actually do. It just should be a lot cheaper. Must be installed for the correct flow direction. Yeah, you can't install backwards. It won't work at all. Many manufacturers, many brands. It used to be there was only 3 or 4 manufacturers of these, and now there's tons of them, lots of them. This is a simple one. It's just a piece of pipe with that single plunger in there. It's probably a half-inch one. And you measure across here. This one actually has measuring flows on it. A lot of them don't have anything. So you have to get your pressure from a port somewhere. This is another brand. I forgot which one this is. Same thing. This is a threaded connection. It has measurement readings. This is another. This is Grundfos, I think, and this has a spring-mounted plunger this direction. Yeah, this is another one. This one actually has a valve. You'll see these all the time on the hose kits you buy. So this is the balance valve to change flow, and then our shutoff valve. And this is the automatic flow valve, but again, it has a limited pressure range. And this is another one that's pressure that you can actually read. And this is what a flow profile looks like. So here's your flow GPM. I'm sorry, this is flow and GPM. So if your head is down here, it's 0, and as the pressure comes up, it's going to a fixed orifice. It gets to here, the spring starts working, so it keeps the flow constant, almost constant. And once you exceed its pressure, it takes off as an orifice again. So that's how their curve looks. Another beast is a pressure independent control valves. And these are also valves that everyone says, oh man, we don't need to balance those. And that's basically true. They do operate. These are control valves, not balance valves. Now, these are control valves, but I wanted to let you know about the probable issues you might have with these, so you'll need to be able to deal with them in the field. So here's these valve assemblies. This is a Belimo, of course, and it's got a control valve here, and it's got a flow meter upstream. So the flow, what happens is the control system tells the flow meter how many GPM I need, and then it modulates this valve to maintain that pressure. They're really slick. They're really expensive, but they're really slick. And these because these are totally pressure independent. Think of this as a pressure independent VAV box for water, basically what it is. So it's fairly good. I like them. I have had problems with them, so we'll talk a bit about that. Flow meter controls a valve for pressure changes. So if the water pressure changes, some other valve's closing off, then it will close this valve down to maintain its flow as constant. Valve and flow meter are set and calibrated through software, which means all valves must be fully commissioned prior to balancing any part of the system. So, as typical, a lot of times the control contractor's not done when we're out on the field. For these things, they need to be done. They need to be fully commissioned, not just installed and programmed, but fully commissioned through that tool. That's what commissioners never done when we're out there. So, but this needs to be done. This is one thing that's different. You try to balance the system upstream with these running wild, you're not going to be successful. Valve controls GPM required for the load and also sets maximum GPM set point. System does not have diversity. Pumping systems are balanced normally, just like normal. If the system has diversity, then the valves must be overridden closed to equal the diversity amount before balancing the pumps. So this is just like any other system. You can't leave these in auto. If you've got diversity, some of these need to be closed. Where I've had problems with these in the past is where we had 2 or 3 3-inch, and then we had a bunch of regular valves, not pressure independent valves for fan coil units, the rest of the system. And what happened was these was early. This is several years ago. These had a problem being stable. They would begin to hunt because I think the other valves were doing their thing, and this one was trying to be pressure independent, and it was hunting all the time. And eventually, we were never ever successful of getting to work correctly. We had to remove them. They were Bellimos also, but we just couldn't make them work. And that basically is pumps and balance valves. So it's a very short video, but I hope it was beneficial. Thank you for watching. I really appreciate it. Thank you for being a subscriber member, and have a great day, and I'll catch you in the next one.